Hi, I'm Mike Holt with MikeHolt.com, and I really appreciate you taking the time to watch the videos that I'm producing. I do want to just take a moment to give a shout out to God. He's blessed me, and I really want to say a prayer for everybody who's watching this and those that are struggling with so many different levels, and I pray that it just gives you some strength. Now, I'm going to go one more time on the system voltage 3 days in a row. But Brian, before I get there, did you want to say something to our
Oh yeah, Mike,
here?
we got a ton of schools that have been watching, and just a few of them have messaged me, and I told them yesterday and the day before, I give them a shout out if they gave me a message. So we've got Shaw Tech watching, we've got Suncoast Schools in Florida watching, we've got 3 or 4 different classes from Porter and Chester. I've had guys say, hey, great class. We've got people on from Power Design again. I don't think I'm forgetting anybody that emailed me, but I've just been getting a lot of messages from people. They are really having a good time and just saying how much they appreciate you taking the time to talk about stuff that a lot of us have just wondered about for a long time, and it's good to have somebody just kind of step us through it. So just really appreciate that, Mike.
Well, you know what? I think it's so cool. You know, when I'm in a seminar, I'm being paid, right? And I have an agenda, and I've been told what to do, and I have to do that in a given time. When I'm producing live stream videos and I'm producing DVDs, again, as a project, this is unique. This is something that I'm able to things I've been wanting to tell people that it's in my head, but I just don't have the ability to do that. And I do want to thank Dan Herrick. Sorry, I've been saying your name wrong all these years. Dan called me last night because I wasn't happy last night. I left the recording, I jumped on my bike, I rode for an hour out there, and I was just frustrated because I just didn't like the way it went last night. And he said, Mike, he says, you're doing great. So Dan, thanks for that, and I appreciate that. Dan, you're an amazing father and an amazing son, and you're an amazing guy, and you help us so much with our product. So thanks for being on our team. All right, you ready for this? One more time on system voltages from the beginning to the end. I'm assuming at this point when you're watching this video, you've seen the first video, then we had questions on the second video. Now I'm going to bring it all together and summarize it. So if you hadn't done that, you can watch this, but go back and watch 1, 2, 3. And honestly, you should watch 1, 2, 3 all over again. Ready to go? Now, quickly. Okay, transformers. Just conceptually, it's called mutual induction. You have a wire going around a coil, and when you carry current through that conductor, it's going to create an electromagnetic field. That magnetic field in the primary is going to cut the secondary conductor. This is all covered in our theory book. And that magnetic field in the primary cuts the secondary conductors. Its magnetic field traveling through a conductor, the relative motion between the two will cause electrons to flow on the secondary side. Short version, so get the theory book to understand more of what I'm saying. Okay, now there's a turns ratio. The number of turns on the primary relative to the number of turns on the secondary is how we're able to get the different voltages to step it up, to step it down. An example right here is showing you, let's say, just using relationships here. Let's say there were 20 turns in the primary, and the voltage of the primary is 480. What that means that each individual winding turn is going to be 24 volts. In other words, that's the effect of that section. And then on the secondary, let's just say there were 5 turns, so the ratio is going to be what? 4-to-1 ratio. But each winding is still going to be 24 volts on the secondary because they're really pretty close to each other, okay? So now if you have 5 turns on the secondary at 24 volts, then you're going to get 120. Again, it's not that big of a deal, but there is a relation between the primary and the secondary voltage, and it's that ratio that gives us the different voltages to step it up or to step it down. Quick, go real fast. Single phase, 120, 240 volt, 3-wire system. Okay, you bring a line 1, a line 2. I don't see my neutral here. Oh, okay, we're just bringing a single phase to the transformer, okay. Okay, that's a primary, whatever the voltage is, we don't care. 120, 240 on the secondary. We take the midpoint of that one winding, and then we bond that. That means that we're going to ground that winding right there, and then we connect it to a grounding electrode, and line 1, line 2, and a neutral. 3-wire. Single phase, one winding. Here's an example of what it would look like. Primary, it's basically, it looks like this, just one phase. Okay, well then the secondary is what, 120 line, just half of the way, and 120 half of the way. Well then the whole way is going to be 240. right? So 120, 240, single phase. You take the secondary winding, which is a separately dry system, and we're going to bond it to the case, and then we're going to take both the case and that XO terminal, and we're going to ground it to the earth, either at the point of the separately dry system or the first disconnecting means afterwards. But wherever you do the system bonding jumper, that is where you have to do the grounding electroconductor. Or wherever you do the grounding electroconductor, that's where you have to do the system bonding jumper. But it can be either one of those two locations in a transformer here. All right, looking at the example here, what happens is a fault, a ground fault, which means defined by Article 100, which gives us a definition. Electrons leave the transformer, go to line 1 overcurrent protection device to get to the enclosure. There's a ground fault. Ground fault current is going to the source. Fault current, ground fault current is not going to the earth. You can just watch the path here. Current goes to the enclosure, goes to the equipment grounding conductor. From the equipment grounding conductor, because it's on the supply side of this secondary disconnect, that's a supply side bonding jumper. And then the supply side bonding jumper. And then we have the system bonding jumper. And then, of course, the whole thing is going to be grounded. So now we're grounding the secondary. We're providing a system bonding jumper to provide the effective ground fault current path for that fault current to get back to the source. And what does it do to the overcurrent device? Probably opens it up in about 0.03 seconds, depending upon the type of overcurrent protection device that you have. Guess what? Fault current is not going to ground, guys. So forget about all these ground rods you guys are driving. Okay? Now let's just look at it again. Well, electrons leave the one phase of the winding of the transfer, goes to the overcurrent device, there's a ground fault. This is mathematics here. Now you can do the math, you can show the math. Okay, well you're at a 12, what is this? A 12 gauge wire out here and a 12 gauge wire out there, and you go to chapter 9, table 9 in the back of the code book, and you get the resistances of the conductors, or you actually get the resistance of the conductors, and then you have the system bonding jumper, a supply side bonding jumper, and you have the system bonding jumper. Electrons leave the source. There's a ground fault. They travel on the effective ground fault current path to get back to the source. Provides a low impedance path to do what? Open the protection device. Now, if I said that too fast, that means you didn't see the first video and you didn't see the second video. You should be able to understand what I'm saying now. Mike, you go too fast. Well, not if you watch. If this is your third time at it, don't. And by the way, there was some math calculations. You can take a look. All this stuff is from my bonding and grounding book or my theory book or my understanding NEC. 3-phase, 120, 208, 4-wire Y system. Now look, somebody has decided which system they're going to be using. Single phase, 3-phase, 120, 208. Somebody's making that decision. And a lot of that decision is a function of the electric utility, what they have available at that location. So don't worry about, well, how do I know all these different voltages? Well, if you're not designing them, it doesn't really matter. If you are designing them, then you're going to have to get with the utility. You're going to have your criteria. When do you go to 277, 480? When do you go to 120, 208? And that's not the scope of this program. All right, 277. I'm sorry, this is going to be 120, 208, 4-wire. Well, 120, 120, 120. We have 3 phases and a neutral. There's 4-wire, no problem. Okay, 120, 120, 120 is going to be the phase voltage. Well, then the line voltage from here to here, which would be from here, which is here, to here, which is here, it's 120, 120, and 120. But what's the voltage between line 1, let's say, and line 2? Well, you know that because it's not 120, 120. It's 120, 120 vectorially by 120 degrees out of phase with each other. And we've talked about that. That was 20.8 inches. Remember that? Or 208 volts. We talked about be very careful that when you're selecting protection devices, that if it's a slash rated breaker, like a 120, 240 volt slash rated breaker, that it's suitable for the system. Now, the maximum voltage between any one line, this line right here, I think this voltmeter is, yeah, right here, okay. Between, let's say, this line right here and ground is 120. And 120/240 means the maximum line to ground voltage of a fault is what it's talking about, is 120. Well, then, of course, in a Y system, that's fine. Now, the higher voltage of the slash means the maximum phase-to-phase voltage under a fault condition. Well, 208 is the maximum, so guess what? A 120, 240 volt slash rated breaker is perfectly fine to be used on a 120, 208, 3-phase 4-wire system. Now, straight rated breakers, a straight rating on a breaker means that it really is a 240/240. okay, in 240/240, which means that the maximum line to ground voltage is 240 and the maximum phase to phase voltage is 240. Well, we're not going to be using a straight rated breaker because they're not that common and they're not necessary and they cost more money for single phase anyhow. I'm adding a new graphic a little different than what we've been doing is to try to show you. Remember we talked about that delta Y configuration? Well, in reality, it is 3 separate phases. That's why it's called a 3-phase system. So there are 3 separate transformers. And it's just a matter of how they wire. Look, there's only 2 wires on the primary of this one phase, and there's only 2 wires on the secondary of the one phase. Well, if the primary is 480 coming in, and you had a 120 going out, and you wanted to get a 120 208Y secondary, well, it's a delta. So then what you do is this. This winding is connected to that corner of the winding, which connected to that corner of the winding, which connected to that corner of the winding. And you watch this video later on, you can slow it down and stop it. You'll see that this connection is to that winding. It goes to this winding. It goes back to this winding. They're actually in series with each other. And then, of course, we have points that we're making conductors coming in on the primary side. So here are the 2 wires on the primary of that one phase. Here are the 2 wires on the primary of the second phase. Here are the 2 wires on the primary of the third phase, and this is all done internally of your transformer. All you're going to do is going to see this terminal. Well, it's not going to be L1, L2, L3. It's going to be probably H1, H2, and H3. And on the secondary, you're not going to see the 2 wires for the secondary winding of the one, and then the 2 wires of the second phase. You're not going to see the 2 wires of the third. It's all going to be done internally. And guess what they do here? If it's a Y system, then all 3 of them are connected together at one point, and then the other points have different conductors connected. You're only going to see X1, X2, X3, and probably XO. They're not always universal, but that's a pretty common way. So now you're bringing in line 1, or you're going out line 1, line 2, line 3, you're coming out with a neutral. But this right here, look, this is connected to this one, which is connected to that one, which is right there. I don't have time to spend more time on this. We covered that in theory, but at least wanted to give you an idea that a 3-phase is 3 separate physical transformers that are single-phase transformers that are just kind of connected together. All right. Okay, you have a question real quick?
Yeah, one of the guys, Daniel, says, would you need a straight-rated breaker on a high-leg system if any of the poles...
Well, 1 second. We're not going to talk about high leg. When we get to high leg, we'll talk about high leg. We're only on Y configurations. Okay, so now on the secondary winding, just to remind you, 250.38.1, which deals with the grounding and bonding of transformers on the secondary side, it says that your system bonding jumper and your grounding electroconductor connection could either be at the transformer, as the word here, or at the first system disconnecting means. But they both have to be together. System bonding and grounding electrode connection either at the system or the first disconnecting means. Staying on the Y, delta Y configuration. Well, 3-phase, Mike, is the fault current get back to the source? Guys, it's only 3 individual windings that are just kind of connected a certain way, and the electrons will leave on the secondary, and the electrons have to get back to the secondary. That's how an electrical circuit operates. It's not that complicated. Electrons leave the secondary, go to the overcurrent device. There's a ground fault. Ground fault current is not going to ground. It's going to go back to the winding itself that it came from. And it goes along the equipment grounding conductor, supply side bonding jumper, the system bonding jumper. All those 3 is part of the effective ground fault current path as defined in Article 100. And make sure you go to 250.4A5 as well. Clear the breaker, maybe in 0.03 of a second, hundredths of a second. All right, but what happens if a person doesn't install the system bonding jumper? Well, guess what you have? You have an ungrounded system, which was not intentional. And since you have a neutral, it's 250.20 that talks about what systems are required to be grounded. If you have a neutral, and if it's a 120 208 or 277 480, it requires that system to be grounded. So this is a violation of that rule. In addition to that, you have an ungrounded system, and we didn't get into, but Beeman's book talks about ungrounded systems and the problems. There's like 9 different scenarios where you'd have a problem with an ungrounded system. That's why it's not a favorite system. So you're going to create problems with an ungrounded, and you can't clear a fault because there's no fault return path. Also, using this graphic as an example, if you didn't have the system bonding jumper, well, then it's a floating system. If you take a voltmeter between line 1 in the case and line 2 in the case and line 3 in the case, having a voltmeter that has a low impedance setting in there, well, then you're going to say 0, 0, 0. But if you go line to 1 to 2, 2 to 3, or 1 to 3, you're going to see that it's going to be 208. And if you go line 1 to the neutral terminal, it's 120. Line 2 to the neutral, 120. Line 3 to the neutral, 120. See, you should be able to, with a voltmeter, and having the knowledge we've had on these 3 different videos, be able to get to a spot and realize, okay, I got nothing from line 1, line 2, and line 3 to the case. But I get 120, 120, 120 to the neutral, and I get 208, 208, 208. Well, guess what we have? We have a system bonding jumper that's missing. And it can create other issues, but we're not going to get into those. But hopefully this is what you're getting. It's a review. What happens if you install the system bonding jumper both at the transformer, which is where I've been showing them in general, and then somehow a person sees that strap or that screw and saying, okay, well, there must be a reason they got that in the panel, and then they just kind of put that in the panel, and they make a connection here at the system, separately drive system. Well, now you're going to have parallel paths for neutral current. You see, every single system is to be bonded and grounded at one time, which means you take that neutral and you bond it to the case, and then you take the case and the neutral and you ground it. You don't ever do a neutral to case ground again, because then your neutral and your equipment grounding conductor are in parallel. Violates 250.6 objectional current, violates 250.142. It'd be a hazard. Again, it's not the place to talk about all the details. Where do you make the connection of the grounding electrode conductor? Well, you either make it at the transformer. The first disconnect means code doesn't care, but you'd have to put the system bonding jumper at the same location. Does that grounding electrode conductor have to be connected directly to the XO? No, because if the XO is connected, let's say, to the grounding bar in 450.10a says you have to have a grounding bar in the transformer. Well, if you're going to go XO to the grounding bar, why the heck would you run the grounding electric conductor all the way up to the XO when you got a grounding bar there and it's required to be there? But you could if you want to. It doesn't really matter. Either way is fine. And there's an example of 450.10a. You can see this grounding electric conductor is connected right over here to that grounding bar. And this right here is the equipment. Here's the equipment grounding conductor coming to that bar on the primary, and there's an equipment grounding conductor on the secondary. And then, that's probably, well, we have a system bonding jumper not shown here. All right, 277, 480 volt, 3-phase, 4-wire. Hopefully these words are not like freaking you out. You know what? This is what the first-year apprentice should be learning. They should be understanding voltage systems. At least you should learn this in electrical theory. This isn't something your entire career you didn't know what was going on. That's why I'm so excited that I'm able to do this, to get you this information that, when am I going to be able to do this? This is too cool. All right. Sorry, I'm getting a little excited. I've been told, slow down a little. Okay, we got a 277, 480 volt, 3-phase, 4-wire Y system. Right, 1, 2, 3. What color code? Oh, brown, orange, yellow. Code doesn't really care. Brown, purple, yellow, because you're thinking yellow, orange can't be used for the Hilux. You put purple. Doesn't really matter. You can use orange. You can use purple. You can use any colors you want to. Let's talk about the voltages. Line to neutral voltages are 277, right? And line to ground, because neutral is bonded to the case, well, then line to ground, line to neutral at the same points, it's going to be 277. Between the two phases, or between the two lines, rather, it's going to be 480, because it's 277 plus 277 vectorially added at 120 degrees out of phase with each other. And if you put a tape measure there, then we talked about that. 480 volts, line to line. When do you use 277, 480? When you have it, when utility has it there, and you got a lot of line and neutral loads, and you want some high voltages, and you're willing to put some transformers to drop it down to 120, 208, so you can pick up some receptacle loads and maybe some other lower voltage loads. But you're thinking, hey, I got a school here. I'm not making a school 120, 208, 3-phase, 4-wire. I'm making it, I'm going to make it 277, 480. That's a designer's decision. What happens if the ground fault? Fault current doesn't go to ground. You don't drive ground rods. You don't go to ground, right? Electrons leave the source, travel back to the source. They leave the winding, they go to the overcurrent protection device, there's going to be a ground fault, it gets to the equipment grounding terminals, on the equipment grounding conductor, to the supply side bonding jumper, to the system bonding jumper. All this green stuff is called the effective ground fault current path, which is a low impedance from the point of a fault back to the source. And it says, for the purposes of opening up or clearing the overcurrent device. That's Article 100, definition of an effective ground fault current path. Electrons aren't going to ground. All right, how about a 120, 240 volt, three-phase, four-wire, high-leg system, delta? Well, you got a line 1, line 2, line 3, and a neutral, and the high leg is required to be colored orange, placed on the B phase of a panel board only, not disconnects and not meter enclosures, just panel boards. 408.3 E1, yeah, E1 talks about the location. And 110.15 is about the color. So here's your high leg. Voltage line 1 to the neutral or to the ground point, 120. Line 3, voltmeter, to the ground point, which is the same thing as to the neutral point, you know, that half of a winding, 120. Voltage between line 1 and line 3, which is right here, well, that's 120, 120, straight, right there, additive directly. That would be line 1, I'm saying I want to go line 3, and line 3 and line 1 is 240. So line 1 to line 3 is 240. Line 1, the neutral is 120. Line 3 to the neutral is 120. But the high leg is kind of hanging out here. From that reference point, which is where the neutral point is or where the ground point is, it's going to be 240 volts vectorially added with 120. And if we talked about the ruler and make it, you know, what's it, 24 inches this way and 12 inches that way, and then you make that ruler, you're going to find out it's 20.8 inches, or 208 volts is the high leg voltage based upon the 120, 240 volt configuration system here. Okay? Now, delta, delta, high leg. Look at this configuration right here. Here's a delta. Here's a delta secondary, and then the center point of that one winding, which means you have a neutral here. Anytime it's the center of a single winding, it's going to be the neutral. And you can see the high leg is all the way out here in line 2. I say line 2 because the code requires the orange conductor to be the high leg terminating on the panel board. It doesn't have to terminate, I mean, in the B phase of a panel board. It doesn't have to terminate, in the meter can, it's going to be on the right side. In the panel board, it's going to be in the center. And if you really want to get creative, put the high leg on the A phase in the disconnect. That way everything is balanced. I'm joking, but it's fine to put the high leg on the A phase in a disconnect because that's not a code violation. It's fine to put the high leg on the right side of a meter because that's not a code violation. The only place you are required to have the orange high leg located in the B phase is when it's in a panel board or a switchboard or switchgear. All right, let's look at the delta configuration. Guys, it's just 3 windings, 3 phases, and somewhere internally they hooked it up delta, and on the secondary they hooked it up delta, and they gave you a terminal that would have been XO, and it would have been X1, X2, X3. So you just would have gone there. Now what you could have done, proper PPE, you know what you're qualified, you could have taken a voltmeter on the transformer and find out, I wonder what kind of transformer I got here. Well, go line 1 to the case with the system bonding jumper installed. You should have had what? 120. Line 2 is like 208. Oh, wait a minute now. I got a high leg. Line 3 is what? 120. Okay. What about line 1 to line 2? I'm sorry, let me get back here. Well, line 1 to line 2 and a high leg is 240. Line 1 to line 3 is 240, and line 2 to line... So you can figure out what kind of transformer, if you didn't have a label on there, is what are you getting in there? All right, now, what about a fault? We have a high leg fault, using the worst case scenario. Well, then that's going to be 208 volts to ground. When I say ground, we're talking about where the XO is connected to the case of the enclosure. It's not really ground, but we call it ground. Well, then electrons leave the transformer, go to the overcurrent device. There's a ground fault, travels along. Oh, my battery is getting slow here. It travels along the effective ground fault current path, and then you trip the overcurrent protection device. Now, straight rated breakers. You know what I got to do? I got to take a small little break. Brian.
So nothing like getting put on the spot. We had the phone battery dead yesterday. Now we got the computer battery dead, but this is better. Okay. It's okay because I'm going to say hi to these guys real quick. I got in Massachusetts, who do I have here? Michael Norris at Madison Park Technical Vocational School in Boston. Hi to you and your class. Thanks for joining us tonight. Hold on. He touched something when he moved. Give him a second to check your camera. Check something.
It's coming.
If we got him.
No.
Yep. Okay.
No.
Hold on. We don't have you.
What he was working on was fixing it, but it went back away.
Whatever you touched fixed it, but it went back away when you sat down.
I think it's up by his phone. I started to get something.
Yeah, whatever you're doing is working with it. Try switching to channel B and see if that works for you.
Switch to B.
That's it.
Apparently
Hey, there you go.
It switched to B.
We got you back.
Yep. It was in my pocket. It switched to B. I'm on A channel. Okay, sorry about that. Delta high leg. If there's a fault from the delta high leg back over here, that means the ground default voltage is going to be 208. We would have to use a straight rated breaker anytime you're connected physically on the high leg, because the voltage to ground is 208. Where's it? One second. Right, we don't. Here it is. Voltage to ground is 208, and the phase-to-phase voltage is 240. So straight rated breakers are fine for high leg. Now, if you don't put it on the high leg and you go to line 1 and line 3 only, well, then you can use slash rated breakers. We're good. And here's just an example where if you had a slash rated breaker and you connected it on the high leg, well, then that would be a violation. And then high leg color, 11015, orange. You terminate in panel boards on the B phase. And in the meter cans, it's going to be on the C phase. This is a panel board that would be on the B phase. And at the panel board, you have to make sure you put some kind of identification that the B phase is rated 208 volts. All right, Brian, you had a question on the high leg. What was it?
Well, we've actually got a few questions. I'm going to jump back down to the high leg one. And it says, okay. Would you need a straight rated breaker on a high leg system if any poles of the breaker will land on the high leg?
I just said that. If you connect it on the high leg, the voltage of the high leg to ground in the event of a fault is 208 volts. So you have to use a straight rated breaker.
All right, we've got another.
But if you don't go on the high leg, you can use slash rating. Okay.
We got another one. If the system does not have a system bonding jumper, will the disconnect still work? And before you answer that one, just go ahead and cover this too. What would happen if the ground fault would occur before the secondary disconnect on the secondary?
I don't know what system we're talking about, so let me go back over to something that people can relate to a little easier. So let's go over to a three-phase 120/208 volt system. All right, Brian, so take one question at a time.
So it says, what would happen if the ground fault occurs before the disconnect on the secondary?
Right here. Let me go back. Let me go right here, this graphic. Right here. Okay. If this fault occurred on the line side, okay, let's say it goes to this enclosure right here, ahead of the disconnect. Well, then if all current would leave, it would then go to this enclosure. It would then travel to the equipment grounding conductor along this effective ground fault current path in that direction there, and maybe you clear the primary because it's on the supply side. So that's why you have a supply side bonding jumper. So probably it'll clear the primary side, but it's because it's one winding on the secondary side, but then that current travels on the primary side of 3 windings. So I'm just going to say that's what it will do. I don't know if it's going to clear it or not. It probably will.
Okay, before you move from that graphic, if the disconnect is used for the system bonding jumper, does it need to be service entrance rated?
If you're going to put a system bonding, listen, all equipment is going to be rated for service equipment. So if you're going to have a disconnecting means, it's going to come with a strap. And if you plan on putting the system bonding, guys, if you're going to bond that neutral to the enclosure, then that enclosure has to be suitable to have the neutral bonded to the enclosure, which means it has to come with a strap. So this isn't like a complicated thing. I don't want to put the system bonding jumper and the grounding electrode at the transformer because I want to do it right here at the disconnect. Well, then you're going to get a disconnect that has what? A system bonding jumper. We call it a main bonding jumper, but that's for services, but it's going to be your system bonding. So yeah, you'd have to use one that you can do it, which they make them. That's just the way they make them. You're going to get them that way.
All right, we got one more here. It says, if you have a metal conduit between the transformer and panel, does the ground conductor have to bond to the conduit?
I don't know what a ground conductor is. So when you guys start using words that are slang terms, I don't understand. Brian, see if you can read it again to me.
Okay, if you have a metal conduit between the transformer...
1 second. Hold on right there. Let's assume I physically don't install a system bonding jumper, a supply side bonding jumper here, right, Brian?
Yep.
You with me? I'm going to put a metal conduit between those two.
Yep.
With metal couplings, metal lock nuts. Okay, that is my supply side bonding jumper. So they just said you're running a metal conduit between the transformer and the disconnect. Okay, go ahead.
Does the ground conductor have to bond to the conduit? I think where this is going is the issue, and you addressed this the other night with the bonding bushings.
Guys, let me explain this. The system bonding jumper is where you terminate the grounding electrode conductor. The system, not your supply side bonding jumper. If you put a piece of metal conduit between these two here, that doesn't change your system bonding jumper. And also using terms that don't make any sense at all. So I can't do any more than that question because it's a little convoluted question and the person doesn't understand system bonding jumper. Nothing to do with the metal raceway. That's unrelated.
Well, the only other thing I want to do is I see that Tom Dimitrovich joined us, and I want to say hi to Tom. Hope everything's going good for you, buddy.
Tommy. I love Tommy. Eaton. Got me some good breakers coming, right? All right. We are now going over, we got done with the high leg, and now we're going over, there's a lot of stuff here. Corner grounded delta system. Not that common, but research reminded me, Mike, because of the problems of an ungrounded system, because Beeman talks about 8 or 9 different reasons why you have failures of ungrounded systems and the equipment's associated with that you really want to go with a grounded system. Then they took these ungrounded systems, they just corner grounded them. And so now we're going to talk about, well, how do you do if you do a corner grounded delta system? 3-wire. Okay. Well, you have line 1, line 2, line 3. The grounded conductor, which is right here. This is that corner grounded right here. Actually, it's bonded, and then we ground the equipment, but whatever. That's your grounded conductor. I think the practice is line 2, but it could be line 1 or line 3. It doesn't really matter. So I'm going to say it's line 2 in my example. So therefore, this is going to be a white wire or a gray wire, whatever you want it to be there, or black wire with face tape or whatever it is. That's black, white, red. Again, there's no color coding required by the code, but that might be a common system. All right, got the corner grounded system. And what's the voltage if you're corner grounded? Well, if you're corner grounded, well, then that's your reference point, period. That means that that's 0 because then you take it to the earth. So your system bonding jumper, and then you have your grounding electroconductor, And then the voltage between 0, let's see, this is line 1 to 0 is 240. Line 2 to 0, when line 2 is 0, it's 0 because it's the same point. Line 3, which is this winding right here, is gosh, these windings should be 240. Darn it, I didn't change this graphic here. I didn't get an updated graphic from my coworker. I don't think you got that reference point. So this should have been 240, 240, 240. So that would have been line 1 would have been 240, and then line 3 would have been 240. Okay? We got the concept? Somebody said, well, Mike, you know, if you grounded that corner grounded delta system, aren't you going to have objectionable current flow? Guys, you can only have current traveling on metal parts when it's connected to the grounded conductor at 2 points. Look what we did here on this corner grounded delta system. How many times did we ground that secondary system and bond it? Once. Whether you corner ground it, whether you center ground it, it doesn't really matter. You can't do more than one. So no, there's no, people are like, man, I just don't understand. You're taking the B phase and you're connecting it to the case. I know it's wrong. I know it's not going to work. I know it's dangerous. It's not dangerous. That point is connected to that case. It's connected to the earth and it's all 0. Everything out reference to that is not 0, however. Okay. Fault current leaves the 240 volt systems, travels along the ground fault, the effective ground fault current path. System bonded jumper goes up inside here, bada bing, bada boom, 240 volt fault, opens a protection device. That was it I had on the corner grounded delta system. 3-phase, 4-wire corner grounded delta system. I'm showing a Y delta configuration where you reverse fed a transformer that was delta Y, where you were supplying 480 down to 120, 208, and you decide, you know what? If I get 480 down to 120, 208, I need 480, and I have a 120, 208, can't I just backfeed that little puppy right there? I mean, like, now, supposedly, it's not the best practice to backfeed a transformer. However, you got to make sure the transformer is marked suitable for reverse fed. And you look at the instructions, they show you how to do it. So now, we do not bring a neutral on the primary side of a Y system because we don't need a neutral. Well, Mike, would it hurt if I brought a neutral there? Well, why don't you bring a neutral to 3-phase motors and not use it? So why would you bring a neutral to the primary side of a transformer and not use it? So no neutral in the primary. Secondary is corner grounded. Okay, they're all 480 in this case here, which is correct. 480, 480, 480. Line 1 to ground is this winding here. I probably should mark them like A, B, C in the future maybe. That way I can see it. And that would be, let's say that B phase right there, transformer. That's going to be 480. And then, of course, this is grounded at one time, which means this is called a grounded conductor, not a neutral conductor because it's on the corner. It's not in the middle. That's 0. The other phase is 480, and voltage between phase is 480, 480, 480, 480. How do you clear a fault on a corner grounded delta system? Well, if the phase that's grounded is false again, guess what you have? Objectionable current, right? If you have the neutral, it's not a neutral. If you ground this to the case here, and somewhere over here you have this, your grounded conductor inadvertently ground faulted, okay, well, no, you're not going to have it. Yeah. Well, you're going to have current. Yeah, what you're going to have is you're going to have currents traveling on line 2 back in how the way the 3 phases work, and then you're going to have currents traveling on that. So a corner grounded delta system, if the phase itself grounds again, then you are going to have a grounded conductor connection to the case of 2 locations violating 250.6 ejectional current. But if another phase goes ground faulted, well, then the fault current leaves the source, goes to the overcurrent device, gets the enclosure ground fault, it travels on the effective ground fault current path, and it gets back over to the system, and then opens a protection device. The electrons are never going to ground, guys. Don't be driving ground rods to try to make it safe, because that doesn't make a difference. Another day we'll talk about that. 3-phase, 480 volt high impedance, the best of all systems, except you don't get any line to neutral loads on the secondary, so you can't have. So here you go right here, 277, 277, 277 per phase, and then the system bonding jumper has a resistor or impedance of about 1 ohm. And it looks like this here. You can see how it's like a coil, so it heats up in the event of a fault. And then there's alarms that go off and they tell you, hey, you got a ground fault out there. So here's the alarm on your the 277, I don't know if I said 1 ohm. It's 277 ohm resistor for the system bonding jumper. The voltage from line 1 to basically here is 277, 277, 277, and this to here is the same point there, is 277. Voltage between the lines are 480. How do you clear a fault? Well, anytime there's a ground fault. The key here is what, guys? If you don't have a system bonding jumper, you're not clearing a fault. And if you had a fault at 277, and if this resistor is 277 ohms, then what's the current of that fault? Where I is equal to E over R, E is 277, R is 277, 1 amp. Now that is the system you want to install to reduce any kind of arc incident energy, at least when it comes to a single phase ground fault application. The problem with the three-phase, three-wire, high resistive or high impedance grounded system is that you have restrictions. It can only be installed where conditions of maintenance supervision ensure that qualified persons will service it, number 1. 2, that there are ground detectors installed. And 3, only line to neutral loads are served. So you can only have 480 volt phase to phase, a single phase, or three-phase. Three-phase ungrounded, 3-wire delta secondary. Oh, I thought I already covered that one. Oh no, that's ungrounded. Yes, Brian?
Just a quick comment from
Okay.
Eric. He says, while fault probably wouldn't melt the fuse, depending on the voltage, they use relays for many other reasons so that the ground fault can, looks like to actuate devices and set settings. So it looks like
Okay,
on
so
a resisted grounding, they're using it also to actuate different types of relays and probably initiate disconnection and safety sequences.
yeah, this is not something you go out and you buy a resistor 277 ohms and you stick it in there. You're getting a high impedance grounded system. And then, of course, you follow the instructions. This is just showing you a piece that's within the cabinet itself. Okay, so there's your resistors within the enclosure, and the enclosure has meters and relays and controls and what have you. It's a cool system. I love it. Three-phase, 3-wire, 480 volt ungrounded system. Well, here's your ungrounded system. The problem with ungrounded systems is, I won't say they're unstable, but Beeman's talks about there's 8 or 9 different scenarios where when you have a floating system like this, there's restriking ground faults, there's ferroresonance conditions on situations, and there's lightning and static. This insulated winding and all the insulated conductors are kind of like floating in the air, and they end up getting a charge. And they keep getting a charge and high enough till it gets about 6 or 8 times the rating of the actual line to ground voltage, or rather line to line voltage, whatever it is, and then all of a sudden it discharges. Well, when it discharges in motor windings and in relays and things that don't have the same insulation properties of conductors. So it damages equipment. So ungrounded systems, I won't say they're unstable, but they're not desirable. Unless there are applications and places like I think in ships and other locations, but I don't know enough about that. Somebody decided that's what they want, okay. So what does it look like? Well, if you have an ungrounded system, you're going to have a ground detector so they can know that something happened. We talked yesterday about the lights that back in the 40s and 50s, they used lights. Today they use ground detection systems. You know, you can see something like that, okay? Well, years ago it had lights, the way they were configured. And the lights were, I think they were 575 volt lights on a basically 277 would be I don't know what the voltage is with the ground here. I don't know what the voltage is of the ground. But what it was is less than 575. So the lights were dim. And then in the event of a fault, then I guess, Brian, one light went off. No, did it get brighter?
Yeah, the light that faulted went out and the other ones got brighter.
Okay, the fault went out and the other ones got brighter. Meaning, okay. So we don't really care. That's old stuff. So some of you guys know what I'm talking about. How do you clear a ground fault? Well, if you have an ungrounded system, when there's the very first fault, then there is no fault. And there is no fault current because it can't get back to the system. Ground detector goes off. If you don't clear the fault before a second fault occurs, now you have a phase-to-phase fault. That's why the code says for ungrounded systems, that you have to make sure that all the metal parts are actually bonded together just as if it were a grounded system for the purposes of that all those metal parts would be serving as an effective ground fault current path. Other voltage systems, there are zigzag systems that actually you derive a neutral. The other ones we're not deriving neutrals because they're just lugs, we connect to them. There's open delta systems that we're not, these are unique special systems that we're not going to talk about. I don't think we have many of those new today, and I'm not going to get into that. And then you have the old two-phase, five-wire systems, and I'm not going to get into that. Man, we've done this 3 times. I'm done. Really, I'm done. I can't, there's nothing else left there. Haven't been able to sleep trying to figure out how to make it simple. And I thought I could do this in 20 minutes.
You didn't.
Didn't do it.
Have you got time for a couple questions, Mike?
Yes, we have time, and then I'm going to try to jump into something different just to finish up the hour.
I got a question from Adrian, and he says, other than the fact that they're both breakers, what is the thing that makes a slash-rated and straight-rated breaker different from each other?
Okay, Tom Dimitrich is on here, and he could tell you what it is. But in simple understanding, there's a term called short circuit current rating. What that means is that everything has a given short circuit current rating. And short circuit current is going to create heat, and it's going to create magnetic fields. Let's just do something simple of a breaker. If a breaker is rated for 10,000 amperes, well, it's rated for 10,000 amperes at a certain voltage. So that current is a function of a certain voltage. And so let's say at 120, it's rated for 10,000 amperes from line to ground. Well, if you have a higher fault current line to ground than 10,000 amperes, well, then it's going to get hotter than it was designed for, and the magnetic forces are going to cause this thing between the other two faces to move around. So this is an engineering decision. So when they engineered that breaker, they said, okay, let's test line to ground faults. And it was rated for 10,000 amperes for 120, and they tested it at 120. Then they tested phase to phase on the breaker at 10,000 amperes. Okay, at that voltage, that breaker, so everything has an ampere rating at a given voltage. And so that's a configuration. So if you want to know more, well, how do they actually, I don't know how they test it. You know what's important? You better understand all the different voltage systems that you could possibly run into. You better know what the voltage line to ground, because you can just take a voltmeter, you can check that. And that's going to be the lower of the two voltages. And you better make sure that that slash rating, that lower voltage is equivalent to that one thing. And guess what? You're not putting a 120, 240 volt slash on a high lay conductor. But you can put it on line 1 and line 3 because that maximum line to ground voltage is 120. But line to line, they were 240. So guys, sometimes you got to be careful that you don't throw more in there and then you lose with the essence what's important. So just be careful. Yes.
Okay, it looks like the last question, you may want to send them back to yesterday's and Tuesday's videos. They're looking for you to elaborate on auto transformers again.
We covered auto transformer yesterday, and there isn't anything to elaborate. You buy something, it's single phase. And apparently they don't really make 3-phase auto transformers. And so I'm not going to get into that. So an auto transformer is, and we covered this yesterday, the very last 10 minutes of yesterday, is that you bring in, let's say, 208, and you want to come out 240. So you go out to the store and you say, hey, I want an auto transformer. What do you want it from? And you mark, that goes input, output, all the different things, configuration, whatever it is, and you pick the one you want.
Yep.
So yesterday, it's just one winding, and you know what? I don't know where my theory book is. Oh, I gave my theory book away to a guy working in my house today. So it's in my theory book.
All right.
That's it. I got about 10 or 15 more minutes. Ready to go? One more topic. I don't want to see voltage anymore. I hope, and I apologize for yesterday that it wasn't because we had some boo-boos, and I apologize. I didn't connect that one. But it's okay. We're good now. Okay. Grounding electroconductor size. We've already hit this once before. A quick one. Mike, section 25060A says that the grounding electroconductor to a ground rod is never required to be larger than 6 gauge. Why? Well, let me go over here. How many amps you think is going to go to a ground rod? We just covered all kinds of systems. We talked about every single system about a ground fault, every single system. Where the currents go to every single time they clear a ground fault. Every single time. Did they go to the earth? No. See, you guys, including myself at one time, you have no clue what this wire is for. Probably 99%, well, I'm saying 90, depends on whether or not you've ever taken my bonding and grounding classes. But other than people that have taken my bonding and grounding class, you know what? It's going to a ground rod. Guess what you're not carrying? You're not carrying current to a ground rod. You're not carrying fault current to a ground rod. So what the heck are you doing to a ground rod? That is called equipment grounding in this particular case. And when we get the transformers, we saw that was actually not the clear fault. That was called system as well as equipment grounding. We're not going to cover that right now. So sorry about that. That'll be another time. Don't know when I'm going to be covering. So here's what the code says. So make it easy for you right now. 250.66 tells us that when you are required to size the grounding electric conductor, services, remote building, okay, 250.24, okay? At services, require grounding electric conductor. 250.32, 2020 code, requires a grounding electric conductor. Services, service, oh, I'm sorry. 250.33 is a remote building. 250.24 is going to be your services, and 250.30 is your separately drive systems, which is primarily going to be your transformers. They all require a grounding electrode conductor to an electrode that is recognized, and I forget what part it is. It's in 250.50 and 52 and 53, okay? And I'm not going to get into those details. So where you need a grounding electric conductor, you go to 250.66 to size that conductor. Let's read it. Size of the alternate current grounding electric conductor. The size of the grounding electric conductor at the service, 250.24. At each building or structure supplied by a feeder or branch circuit, 250.32. Or at separately drive systems, 250.30. Or ungrounded systems. See, ungrounded systems, you need a grounding electric conductor to go off of the enclosure. And that's going to be a 250.30 also, except it's B. Shall not be less than given in the table. So you go to the table. Except as permitted in 250.66A through C. That's where people screw up. So what does 250.66A says? Connections to a rod, pipe, or plate electrode. Probably we're not putting pipes in the ground and making that an electrode anymore. We're not putting plates in the ground, making that an electrode anymore. We're just going to put a rod. If the grounding electric conductor or bonding jumper connected to a single or multiple rod or any combination of them, and it does not extend to other types of electrodes that require a larger size conductor, the grounding electric conductor should not be required to be larger than 6 gauge. I think they kind of screwed the language up in the 2020 code. Let me tell you what it said, and let me tell you what it says, even though it doesn't seem that way. It says this. You're running a wire to a ground rod, and you're supplementing that ground rod with another electrode, another ground rod, then that wire doesn't have to be larger than 6 gauge. 2,000 amp servers, 4,000 amp servers, 400 amp servers, it doesn't matter. It's not the clear fault, so we're not trying to size it because of the size of the service. It has to do with system grounding, the purpose 250.4A1, and it has to do with equipment grounding 250.4A2, which is a whole other conversation. So what would I always do if I put a couple ground rods for the service? A 6 gauge wire, I don't care if it's a 400 amp, 800 amp, 1200 amp, I don't care because that's what the code tells us. Then it goes on, if you read, it's except as A through C, let's go to B. B has to do with the most common electrode that we're probably using today, which is a concrete encased electrode, rebar. Well, then the largest wire for a concrete encased electrode is going to be 4 gauge. Because the rebar, again, we're not trying to clear a fault. The electrons aren't going anywhere. This is system grounding and equipment grounding, not the clear fault. It's 250.4A1 and 250.4A2. So what size wire would I run to a concrete encased electrode regardless of the size service? 4 gauge copper. Wouldn't put it any bigger, it's not required. Then what's the table for, Mike? Well, the table is if you don't comply with 250-66 A through C. A is a ground rod, B is a concrete encased electrode, 3 is a ring around a building, which is stupid. Hopefully nobody does that. But if they put a ring around a building, then whatever the size the ring is, that's the large size wire you have to run to the grounding ring. Okay? So if it's not the case, if it's not any of those, let's say you go into structural steel, then you have to go to the table because it's not a ground rod and it's not a concrete encased electrode, which means you have to go to the table unless it's a ground rod or it's a concrete encased electrode or the ring. Does that make sense? So now it would then be the full size. So in this example here, if we have 600 amp service and we're parallel 2 sets of 300 kc mills, and you go to the table and you look up the table for 600 kc mills, and it tells you 1/0. Well, then I'd run a 1/0 conductor here. You know, Mike, something's not right here. You got a 6 gauge wire to a ground rod. I'd like to see a 4/0 there. And Cadwell, that puppy right there. That's the way. Because you're a dinosaur. Of course you think that. Because you don't know the code. You're not comfortable. You've just been doing it. Guys, I need leaders here. I need you guys after me. I need you to be able to know what the code is. I don't want you being a dinosaur as an inspector going out there, I don't care what that code says. In my city, you're going to be going to that table. I'm like, oh my gosh. How terrible is that to the industry when you don't know? Listen, you're an electrician. Don't you think you should know the code? You're a master electrician. You're an inspector. You're an instructor. You're an engineer. You're the people. You're the individuals that are out there to protect the public. We need you to learn your code. One guy said to me, oh man, if you learn theory, you won't even know the code. I'm like, oh my God. Please, stop being a dinosaur. Get your code book. Maybe get a product of mine. By the way, tonight, it's real important, if you can, any of our courses at our library at 30% off. MikeHolt.com. Go to the shopping cart and put on the code LIVE, and you can get 30% off the library. Okay, hopefully that answers that question. And then we're going to go to Tuesday. I got some pretty cool stuff coming up next Tuesday.
Looking
By the
forward
way,
to that.
next week we start at 6 o'clock. That's going to be our final time, and we're going to be going for at least 4 more weeks. So we'll be going to go every single week in May. And the reason we've been moving the time is for me to try to find out how it works out. When we start at 9 o'clock Eastern time, Brian didn't get home till 12 o'clock at night. And that means he's worked all day long. And then he has 3 nights a week going to 12 o'clock, and it's not fair to his family. So we cut the hours down to 7 o'clock Eastern time. And Brian, you're getting home, what's it, 7 o'clock now Eastern? So you're getting close to 9 o'clock.
10, something like that,
home.
yeah.
Okay, so we've decided for the purposes of being sustainability-wise, I'm in New Mexico. So it's not a big deal for me. But it's an important thing for Brian, for he can work, get it done. We start at 6 o'clock Eastern Standard Time. We get done about 7 o'clock Eastern Standard Time. And Brian can maybe get home 8:30.
I've got a couple more comments, Mike, also.
Without Brian and his team putting this together, the quality would not be the same. You know, and we're just not going to be able to get it out there too. So I want to thank you guys for watching me and for putting up with me. And sometimes I make these mistakes. I'm not happy that kidding me. All right, Brian, go ahead.
All
Last
right,
couple
well,
questions.
these are going to kind of be a lead into next week, actually. I have, David Sanford says, I'm an apprentice electrician. Can you give me the best book to start reading?
Okay, great questions. I've been getting a lot of career questions, and I posted them all away. So let me tell you what the system starts in May. Tuesday, 6 o'clock, technical. Wednesday is career. Thursday is technical. And it's somewhere in the schedule. If it's not there, it should be on MikeHolt.com/live somewhere in there. So let me tell you what's going on. If you're an apprentice, or if you know an apprentice, if you're an electrician and you've never gotten your journeyman's license, I don't care if you're 51 years old and I don't care if you're 22 years old, but you haven't gotten your license. First of all, if you go to an apprenticeship training program, that program should automatically train you, and when you get to the end, you should automatically pass the exam without a problem. Most apprenticeship training programs, probably in the United States, use, for the 4th year, they use by exam prep book. Pretty much. That's IEC, IBEW, other independent apprenticeship programs. And so if you take an apprenticeship program and it uses my curriculum for the 4th year or the last half of the 4th year, you should be able to pass your exam easy. But you know what? I didn't go through an apprenticeship program. I didn't even finish high school. I was a dropout. So I didn't have the opportunity to get into a program because I didn't even have a high school degree, so I couldn't even get into a program if I wanted to. And somehow I was able to maneuver and manage. My son, he'll be with me next Wednesday night. He didn't finish high school. And, you know, I mean, he didn't go to an apprenticeship training program. And I had a gentleman, I just have an email. Let's see, Brian, if you can, let me see if I can open up that email. Come on. And I'm going to show you an email. I just got the email today, and it really ties into what I'm going to be covering next Tuesday. And let's see if it's going to be James. I don't know how big that can be. Oh, I can open it. All right, a short version. He's told me how our program has really helped him, and he says, if there's one thing I try to tell my guys is that if you can learn this trade, he says, if I can learn this trade, I mean anybody can. I'm nothing more than a wire pulling grunt, and I'm not ashamed to say it. I never went to trade school. I can't do math to save my life. I can't even write a sentence without spell checking bailing me out. But I'm a good electrician, and I'm proud to say that even more, I understand transformers, bonding and grounding, motors in the NEC, and all of that. That's what's important. So what we're going to do, starting next Tuesday, let me get back over here. Next Wednesday is your career. So let me tell you what it is. Next week is an apprentice. Well, first of all, it's going to be about getting into the trade. So if you know anybody that maybe would want to be an electrician, have them watch next Wednesday. If you know somebody who's an apprentice or somebody who's in the trade that hasn't made the decision to get his life, man, how are you going to get this guy motivated, Mike? Have them watch next Wednesday. If you are, the following week, if you are a journeyman electrician, you've been licensed, and you're working as a journeyman electrician, listen, you need to take your career up. That's the second week, is journeyman electricians. And then also we're going to be talking about instructors on the second week. I'm going to be talking to instructors how to take your career. On the third week is going to be master electricians. What do you do now that you're master electricians? Where do you take? On the fourth week is going to be electrical contractors. You guys, you know, everybody thinks you guys are making all kinds of money and it's easy and everything like that. Well, it's hard. And so on the fourth week, it's going to be, and if anybody is that you know, if you're a master electrician and you have somebody that cares about you, have them watch the program with you, because I'm going to try to help them understand how are you struggling if you don't have a license, and if you're a journeyman, and so other people could be, I didn't know that's how you feel, that's what you deal with. So this is a career opportunity. Next Wednesday, I'm an apprentice. I don't know what to do, how to get going. I've been working in the trade. I'm a journeyman. Where do I take it next, Mike? I'm a master. Hey, I'm working in, should I go to engineering school? You know what I mean? Should I go to college? You know, should I be an electrical contractor, an electrical inspector? All these career moves are going to happen on Wednesday nights starting the first week in May. That's the plan. 6 o'clock. So Tuesday technical, Wednesday career, Thursday technical for the next four weeks. Are we done, Brian? I think.
Mike, we're done. We're ready to call it a night. At least I am.
Are you kidding me?
We'll try for batteries and power
next week.
Tuesday.